The history of art is written by the tools used to create it. When the mechanics of image production shift, the aesthetic output follows. In the mid-19th century, the invention of the camera severed the painter's obligation to strict representation. Mechanical lenses could capture literal reality faster and with greater optical accuracy than the human hand. Rather than competing with the lens, painters like Jean-Baptiste Camille Corot absorbed its optical quirks. Corot began painting the virtual shadow caused by moving objects during long exposures and the feather halo effect from strong backlighting. Reproducing these mechanical artifacts on canvas established the visual language of the Impressionist movement. This process of technological integration accelerates through the 20th century. To understand the modern canvas, we have to look at how artists moved into three-dimensional space, adopted mechanical printing, and eventually utilized digital computing. New devices do not destroy artistic tradition. They force an evolution by altering the physics of how visual data is captured, structured, and displayed. Before software could generate virtual environments, mid-20th century artists began engineering physical ones. They sought to break visual media out of the flat, bounded rectangle of the frame. This effort formalized into installation art. Instead of a discrete, isolated object placed on a pedestal, the artwork became a site-specific, three-dimensional sensory experience. In 1958, Alan Capro defined this approach as an environment. He constructed immersive indoor spaces, referring to them as project art, where the physical room itself was the medium. Capro argued that by bypassing isolated objects and taking nature itself as a model, artists devised art from the sensory stuff of ordinary life. This shift from making things to engineering entire sensory fields provided the conceptual transition necessary to move from physical rooms to digital simulations. While artists were expanding into physical rooms, the industrial reproduction of their work was being broken down into microscopic layers. In the pre-press stage of commercial printing, original images are mathematically translated into separated forms for lithography. The four-color process relies on three secondary colors: cyan, magenta, and yellow, plus black. As these semi-transparent inks overlap, they absorb specific wavelengths of light. When all three intersect, they yield mere black. To increase sharpness, a separate black ink is mechanically applied last. The standard CMYK process has a restricted gamut, meaning there are vibrant hues it physically cannot mix. To solve this, industrial presses employ extended gamut printing, introducing distinct orange, green, and violet inks. Adding these three specific wavelengths expands the printable color range dramatically. With a 7-color system, modern printers can accurately reproduce 99% of all classified Pantone colors. By deconstructing a continuous image into distinct, overlapping data layers of subtractive ink, mechanical printing isolated the components of visual media. This separation of data was the exact logic required for computational rendering. That logic fully matured with the introduction of computational processing, specifically computer-aided design, or CAD. A 1972 international conference in the Netherlands formally defined CAD as a problem-solving grouping, a strict integration of engineers, technical operators, and computing power applied to visual documentation. This collaboration yielded two strictly divided architectures for storing digital graphics, the raster model and the vector model. The raster model relies on bitmaps. It stores visual information as an array of millions of distinct colored pixels. Because every single pixel requires its own mathematical coordinate, increasing the resolution demands an exponential increase in disk space. In contrast, vector graphics do not use pixels. They construct images using sequential commands and mathematical curves placed within a coordinate system. Because the software calculates geometry rather than storing millions of static dots, vectors scale infinitely without any loss of sharpness. Digital platforms decouple the artwork from physical matter. The creator is no longer manipulating pigment. They are an architect arranging pure mathematics. These underlying raster and vector architectures power modern consumer illustration software. Digital brushes rely on algorithmic filters to calculate fluid dynamics, simulating the exact behavior of oil paints or wet watercolors. The software executes technical features that are physically impossible on canvas. artists generate flawless geometric symmetry, mathematically perfect ellipses, and isolated layers of absolute transparency. The most significant mechanical advantage is the nonlinear history state. An artist can trigger an undo command, erasing up to 20 previous brushstrokes from the array without leaving a single trace on the digital canvas. Applying traditional paint requires a high-stakes, spontaneous commitment to physical material. A mistake requires chemical removal or heavy overpainting. Software strips away the physical consequences of creation. It provides an environment where endless, hyper-controlled iteration is possible, allowing for aesthetics that require extreme mechanical precision. In the early 1970s, the integration of digital precision with physical canvas took a specific form, a genre known as hyperrealism. While early photorealism aimed for an objective copy of a photograph, hyperrealism takes a more complex approach. It seeks to render the subject as a definitive, living object with a high level of tangible detail. To engineer these works, painters and sculptors rely heavily on mechanical transfer systems. They map out high-resolution digital references using multimedia slide projections, gridding, and precise mold casting. Their objective is to meticulously reconstruct the optical physics captured by the lens, surface textures, lighting effects, and exact shadow definitions. They scan the material world with a camera, process that image data digitally, and then use industrial techniques to translate those pixels back into physical pigment. It is a closed loop of mechanical reproduction. This mechanical loop carries a specific philosophical intent, drawing heavily on the theories of French sociologist Jean Baudrillard. Baudrillard argued against the idea of a simple copy. He focused on the simulation of something that never really existed, a construct designed to pass as reality. Hyperrealists achieve this illusion by deliberately painting the anomalies produced by digital cameras. They map out strict depth of field limitations, photographic perspective distortions, and the pixel artifacting known as fractalization. The naked human eye does not process reality with focal blur or digital artifacting. By manually painting these optical errors onto a canvas, the artist engineers a highly meticulous false reality. From the rigid data layers of CMYK printing to the geometric precision of vector math, visual technology dictates the boundaries of modern media. It has equipped creators with the architectural tools to engineer realities in